Hi guys, so in this video we're going to start to talk about divide and conquer. Specifically we're going to talk about Mergesort and Quicksort. So divide and conquer is a really well-known algorithm design strategy, and the idea here is to divide your problem into smaller subsets, so two or more smaller instances, solve the smaller instances, usually recursively, and then recombine them to obtain the solution to the original or the larger instance of the problem. Right, so in general, you have a problem of size n. You can divide it into two separate subproblems of size n divided by 2, solve those two, and then recombine into the final. So here are some examples, and we'll talk about some of these. So we're going to talk about sorting, Mergesort and Quicksort. Tomorrow we'll talk about binary tree traversals. We might talk about Caroli's algorithm, so that's a good one for multiplication of large numbers, and maybe these other two. Okay, so I'm actually going to switch to some slides that I grabbed from the University of Washington because I like them better. Okay, so first we'll talk about merge sort. So the idea here is that we're going to divide the list into two halves, sort the halves, and then recombine at the end. But we do this recursively, so it's going to be two halves, and then halves of those, and then halves of those, until we get down to single numbers, and then we're going to recombine them together. So this is graphically what it looks like. So you start with the array here on the top, you divide it in half, and then you divide it in half again, and then finally you get these single little arrays, and then you start to recombine from there. So you look at these two and you say, okay, well 18 is smaller, so we're going to recombine in this way. And then when you get to this step, you have two of these subarrays and you recombine them sorted, and then finally at the end you'll end up with a sorted array. So it's actually a really simple algorithm to put together. The coding is really straightforward. So if you have this list, and in here it's integers, so as long as the lengths are greater than 1, or the length of the list is greater than 1, then we're going to create two sublists that are going to be roughly half, so we account for if there's an odd number. And then we copy the elements into each one of the new lists. So that's all this is doing, is just copying the elements into new. And now we just sort these two lists. And finally, when those two are sorted, then we merge them. But notice that this sort is a recursive call to itself. So recursively it would come back in, and it would again cut in half, cut in half, cut in half, until we run out of list. The list that come in is less than 1, and then finally we hit these merge into statements to recursively finally put all of our sorted mini arrays into our main array. So if we look at this merge into, it's also really straightforward. So here we have our two lists that come out, and then the result is just going to be the final array that we're building. So here we're going to so basically in this first statement, what we're looking for is as long as these two the i's are greater than or equal to the list, so I2, as long as I2 is greater than or equal to 0 at this first start, the list 2 length is greater than 0, then, so basically what this is doing is that if list 1 has a smaller element, then it's putting the first element of list 1 into the result, right? And then it's incrementing I1, right? This is our iterator through the first list, and then the second iterator is I2, and that's the iterator through the second list. So if this didn't hold, if list 1 element was not less than or equal to list 2 element, then we would come down here and we would put the result at I, and we would add the result from list 2, right? Because that's the smaller element, which is exactly what's happening here. So if we come here, these are single elements, so back in our merge into, these would be of 1, so this for loop would just execute once, but it would find that list 2 had the smaller element and put that in there. Well, I guess it would go twice. So as long as, so if we've exhausted list 2, but we have some of list 1 left, then we're going to put it in. And the result is going to be 2. So, I'm sorry, it will run twice, right? Because this is a single element, 2 single elements, so it's going to look to put these 2 in to the new array of size 2. And then here, when we run merge into, these 2 lists are going to be both of size 2, so the final is going to be 4. So it's going to loop through, and it's going to find the smallest elements of each one and recombine them in the right way, so on and so forth, until we get to this step, and that will merge all of them finally together. So complexity of merge sort. So if we break it down into what merge sort is doing, so first we divide the list into halves, then we sort the halves, and then we recombine. So dividing the list into half, we saw that was just of 2 for loops that are, putting it into 2 separate arrays. And then recombining is also n, right? It's just that loop that is moving things into the right place, and it's the size of the list. So whatever the size of the list is at that point, which is n. Okay, so, but the one that we don't know yet, is how much does it take to sort the halves. So we know this is n, we know this is n. And if we go back to our original algorithm, this is n plus n. So it's not times because it's not nested. So we're not at n squared yet. So n plus n plus, well, times, because it's the recursive call, and plus another n. Well, okay. Only kidding. So because this is all in the recursive call, so here this recursively is going to be called whenever this, so however many times this is recursively called is how many times these n's are going to run. All right, so if we look at this, the merge sort, so the first level that we do, we want to sort the whole list, and then we split it in half, and we want to sort 2 half lists, and then we will split it in half again, and we want to sort 4 quarter lists, so on and so forth. So the question really is, how many levels are there? So how many times do we break this down? And if we look at this, so at the very beginning, we have our full array, then we break it in half, then we break it in quarters, so on and so forth. This actually ends up being log n number of levels, right? So until we get to singles, this is all going to be log n. So at each step, we already know we do n work. We do n plus n plus n, but that's still n, right? So we do, this is executed log n times, and inside of it we do n plus n plus n, and this is all done log n times. So that means that our merge sort is n log n, which is an improvement. It's a really big improvement over n squared algorithms that we talked about before, which is insertion sort, bubble sort, selection sort. So this is a good sort. The only downside, or one downside, is that this is not in place, right? So we have to use auxiliary space. So merge sort may not be the best if you want to maintain, if you don't have too much space to deal with, to work with. Quicksort. So quicksort, remember our partitioning algorithm, our select. So this is kind of going to bounce off of that, and it's going to just kind of take it another step and do the full sort. So again, we are choosing a pivot, and we're ensuring that whatever is to the left of the pivot is less than it, and anything to the right of it is greater than it. And we're going to recursively do this until it's sorted. Right? So if we choose our pivot to be 65, then we're going to partition things so that, we keep our partitioning correct. So everything over here is less than it, everything over here is greater than it. And then now, so that 65 is sorted. Now we're going to sort S1 and S2, right? So now we pick a pivot in here, and we ensure that, everything is on the right side. Well, I guess here, so this is already sorted. So we pick maybe 31 as our pivot, and then we're going to make sure that everything is on the right sides. And then we'll have 2 more little arrays, and then we'll make sure that those are. So it iteratively does this partitioning and movement until it's sorted. All right, so just kind of an overview. The Quicksort, you're going to choose a pivot, and you're going to partition around it, sort the left half, sort the right half. Mergesort, you're going to divide into 2 different arrays and sort both of them, and then recombine at the end. So Quicksort is in place, and Mergesort is not, so you use a lot of extra space in Mergesort. Quicksort, you don't. So let's talk a little bit more. Let's give an example of Quicksort, and then we'll talk about the efficiency of Quicksort and kind of maybe more design decisions of why you would choose one over the other, because they're both very fast algorithms. All right, so let's say that we choose our pivot to be the very first element. So now we are going to have 2 indices that we keep track of, I and j. And we're going to move I to the right, and we're going to move j to the left. And so what we're doing our comparison on, so as long as I is less than, the number at I is less than 5, we're going to keep going. And j the same, as long as it finds elements that are greater than 5, it's going to keep going until it finds a conflict. So I is moving, it finds 9, which is not less than 5. So now it's going to start incrementing j, and j, 8 is fine, 6 is fine, but 2 is not. 2 is in the wrong place. So now we're going to do a swap. Right, we're going to swap 2 and 9. Okay, and then we're going to keep going. So now I moves over, 7, that's another conflict. J, so we're going to move J until we find a conflict with 4, and then we're going to swap 7 and 4. Okay, so now we keep moving. We don't find any more conflicts until we get to the same element here. And once we get to the same element here, J is going to move over 1 more. So when I and J equal each other, it's going to move over 1 more. And we're going to finally swap with our pivot. Okay, so now we have this at the end. It's not sorted, but we have one element that's sorted. And now we're going to sort these subarrays. So now we'll recursively call this, and we'll sort these. We'll choose our pivots and sort those. So this is another example of partitioning. So I'm going to skip the first line. We're going to come back and talk about that. But so we're going to choose the pivot as the very first element, and we're going to set our indices to start with 1 over, and then our second index is going to be high, so that's the I and j. And so now, while index 1 is less than or equal to pivot 2, then we're going to so as long as this element is less than our pivot, we're going to keep incrementing our pivot. If not, then we're going to decrement our second index. And then if we finally, both of these have found conflict, then we're going to swap them, and we're going to increment them again. And then finally, we're going to swap our pivot at the end with where our index 2 ends up. Okay, so pretty straightforward implementation. Here, the reason that you do this, well, it makes it more randomized. So here, instead of just choosing the very first element every time, we're going to swap the middle element into the first position and use that as our pivot. So we're not always choosing that very first one. For a variety of reasons, empirically, it could be that the array is semi-sorted already, and that might be a really bad place to start using as your pivot. All right, so this is the partitioning. So the sort would be like this. So we have a high and a low. So while these two are not the same, we're going to choose our pivot and we're going to sort the list from, and this is, our start and end, right? So we're going to sort the beginning list and the end list. And then in the sort, of course, we're going to partition again and again and again and again. So it's a relatively straightforward algorithm to implement as well. Complexity of quicksort. So in the worst case, unfortunately, if it's going to be n squared. So if it's really, really unbalanced, that you choose an n that you do your partitioning, that you end up with a 0 array and then n minus 1 array, then you're going to have this really unbalanced tree, and you're going to end up, if you add all these together, these are the total times that you execute. If you add all that together, you're going to end up with n squared. However, in best case, and it can also be, if you read this article too, it can also be proven in average case, but the math gets a little bit messy there. It's going to be n log n. So really, especially if you keep doing this randomized quicksort, where you choose a random or semi-random partition, then you're going to be guaranteed average case is going to be n log n. So this is going to be a really quick algorithm as well. And I think I mentioned in a couple other ones, you're not going to do any better than n log n for sorting. If you do, let me know. But this is the top that we have right now. And just some reminders. So just remember, these are your complexity classes. So n squared is quadratic. This is called log linear, and it's pretty good. And I like this, so it's just kind of an example of the growth rate. So if we assume that on input size of 100, all of these algorithms can do it in 10 milliseconds. So this is how it scales. So we have our n squared and our n log n that we've looked at two different sorting techniques. And look at here, we are at 2.7 seconds, where this is 25.6. So maybe not horrible, but you're going to sit there and you're going to notice it. And then if you get even more input size, so this is a relatively small input size, if you grow that even more, you're really going to notice it. So it is a significant improvement over n squared algorithms. All right, guys. So let me know if you have any questions. Get started on your homework. Finish up your homework from last week and get started on this week's. Thanks, guys.